here. So that's on YouTube. And yeah, I think I'm just gonna start recording and we can just give it another minute.
So, sounds good. And so I was planning for around a half hour. Does that seem about right for you?
Yes. And yeah, a little bit of time for questions, but should be fine otherwise.
Mm-hmm.
Yep.
Cool, that sounds good.
Yeah, I'm just gonna send everyone a reminder so we can have like a couple more people in case they're hacking and they don't they don't see this is happening.
Mm-hmm.
But yeah, how is your weekend going, Paul?
It's good. Happy to be able to kind of see what everyone's up to this weekend with the hackathon.
Yes.
Yeah, it's been kind of a wild adventure, on my own part in the last few years, doing kind of taking inspirations from physics, doing interpretability work, and yeah, it can all kind of like
Yeah.
there's kind of some recursive self-improvement. Like once you get started, like things kind of take away and take a life of their own. So it's been an adventure, and this weekend's been nice. Yeah, how about you? How's your weekend going?
Yeah, going well. I'm glad I'm finally at a place where internet is good. I'm based out of Germany, and the German trains are notoriously bad and the Wi-Fi. But awesome. I think more people are trickling in. I'm just gonna, start us off and then you can get started because I think we also have another speaker after you. And so, yeah, hi everyone. Thank you so much for joining in. I really want to introduce Paul here, who's also a theoretical physicist and was also the co founder at RIT and Simplex AI safety research. And Paul here is going to give the hack talk for this particular challenge. And in case like you are coding or doing something right now, I would suggest that like take like an hour break and listen to some amazing hack talks that are happening. Over to you, Paul.
Cool, thanks. Yeah, so feel free to go ahead and jump in with questions. We can make this a bit of a discussion, and I think especially so jump in because I as far as I'm aware with sharing my screen right now, I'm not going to be able to see questions, so just call out if there's something. Yeah, I'll go ahead. So I have a background in theoretical physics and pivoted into this space of interpretability, and I've been thinking a lot about AI safety over the last 2 years or so. Adam Shai and I started this organization called Simplex, where we're building on some results. Kind of think about like, okay, what does it mean to predict future tokens from past tokens as well as possible? Kind of a simple question, but what would that imply for like what we should find inside of transformers and other neural networks? It's gone really well, so we're building on that. So I think the talk today will be kind of two-ish parts. One is going to be kind of high level, why physics, why physicists for AI safety, and the other will be sharing a little bit more of my journey and our research that we've been up to, in case that can provide some inspiration and starting point. So I kind of, as I was reflecting on this, see two obvious roles for physics and physicists and AI safety. And you'll maybe notice it's not because we have a particular theory that's good. Rather, in my perspective, it's that physicists have a quite useful training in mathematical modeling at the right level of abstraction. So you figure out what the heck it is that you're most fundamentally confused about, and then what's kind of the minimal infrastructure that I would need? What assumptions should I make to kind of see whether the phenomena of interest falls out of that or not? So that's something like even during this hackathon you can keep in mind of like maybe be problem focused rather than framework focused. Obviously, like some frameworks have a lot of cool tools to offer, but I encourage you to just kind of take some, have some courage to be like, you know what, I'm really confused by this. And if it's something reproducible that happens, like there's something that happens reproducibly in neural networks, then there's probably a reason, and then there's probably something that you can, if there's a reason, there should be an explanation, right? So anyway, mathematical modeling at the right level of abstraction, I think is a huge reason why physicists, I think, have a lot to offer here. And then the second one is, well, AI systems and agents are physically embedded, right? There was quite a bit of utility some decades ago when, for example, Landauer was thinking about information's physical, and Feynman and others were thinking, well, okay, what does it mean for information to be physical? Basically, quantum information theory came out of that. It was a new framework of if things are in the physical world, obviously AI systems are, sometimes that's relevant, sometimes it's not, but things like information theory maybe won't be as directly relevant, and we can think of just like what is the thing? What is it for an agent to be acting in the world? And when the world is chaotic, for example, can we predict what's going to be happening here? So there's all sorts of variations on this. So of course, a vision model helped me to make a very convincing graphic of a virtuous cycle here. So this is just, again, kind of homing in on what I want to convey about be flexible with your assumptions, like commit to assumptions, figure out what the mathematical implications are to explain your observations. And if you're successful in that, then often the assumptions also predict other things that you weren't anticipating. That has been the case in my work and in many other successful paradigms. But then eventually you're also going to detect some discrepancies, right? So you're going to modify your assumptions and so on. So you have this virtuous cycle. And then this other point of intelligence being physical, I'll kind of hint at what I see. Why is that important? So for one thing, information theory, I don't know, I come from a background of information theory, chaos theory, and so I love using these tools, but it's kind of, information theory is kind of not the right framework for thinking about neural networks, usually. Sometimes, obviously, yes, you're talking about cross-entropy loss and all that, but if you're looking like inside of the model, something's a little fractured here. So why is that? Well, information theory is about discrete alphabets and communicating with discrete symbols. Here, what's going on inside of a neural network, everything's embedded in this effectively real vector space, and that has pretty important implications. So then things start looking more like quantum information theory, but then again, you're not limited to unitary transformations. So there's some like generalization of quantum information theory that's probably going to be useful, and I'll even hint at a version of seeing success later on here. So this is just kind of a bit to get you taking a step back. Oops, let's see. Okay, so I'm going to focus in now a bit on kind of my journey in this research, and trying to figure out like what is even the nature of computation in neural networks. And we might come to the problem to say we should be finding like the hidden Boolean circuits or something. Is that the point of interpretability? To figure out even like the type signature of like what does success look like in interpretability, we should figure out what is the nature of computation in neural networks, right? And so what I hope you'll come away with by the end of the talk today is that we found that pre-training, just standard pre-training on next token prediction, it induces this belief geometry in neural activations. So effectively, when we're pre-training models to predict the next token, what they end up learning is not only something like a world model, but a way of doing effectively Bayesian updating over the latent states of that model as they're observing more tokens in context. So hopefully that becomes more clear by the end of the talk. And then how could transformers do this? Because transformers are feed forward. There's no obvious way to do recurrent Bayesian updating, so I'll speak a bit to that. And then there's this kind of weird result we have recently, which I think fits in well with this kind of physics-focused audience, that neural networks actually transcend the classical paradigm of computation. And they end up doing things that over the last decade or two, people have been talking about. What's the advantage of quantum computing or using quantum memory even for the purpose of generating and predicting classical stochastic processes? But it turned out a lot of that was just doing computation in a real vector space, and neural nets do that. So they benefit from those, right? So let's go ahead, and if we were to ask ourselves, what computational structures are we building into neural networks when we pre-train them? What would you say? There's all sorts of voices out on the internet of it's stochastic parrots or it's what. Ilya Sutskever has an opinion that I resonate with. Predicting the next token well means that you understand the underlying reality that led to the creation of that token. Okay, so I happen to kind of agree with or vibe with this intuition, but how can we actually set things up, operationalize it, so that we're not talking past each other, so we actually have something falsifiable here? Okay, predicting the next token well, maybe that's just like getting low loss. What does understand mean? What does underlying reality mean? Well, let's say that we just had a very simple toy generator of classical data. So this is just a 3-state hidden Markov model I'm showing on the left. Well, in this case, can we say what we do or don't expect a neural network to learn? What does it mean for it to understand this underlying reality? So we're basically going to say, yes, it will learn this thing, but more specifically, it's not just. So you might think, okay, it's just going to learn that this generative mechanism, it has 3 hidden states, and there's some transition probability. But actually, the lesson that we learn and the thing that we claim is that what neural networks end up learning is not only something like this thing, this HMM as a world model, but a way to do effectively Bayesian updating over the latent states of this model. So that's what they're going to end up learning by pre-training. So just to say kind of simply, a hidden Markov model, you have some number of states. You can think of Markovian transitions over the hidden states, but the symbols, these A's, B's, C's, those are the tokens output. There's a non-Markovian dynamic over those, so you have a correlated stochastic process, even though it's a quite simple generator. So let's put this to the test, that what we're going to predict is that inside the neural net is not like just like three things here, but instead we anticipate this kind of crazy fractal geometry for how the model represents beliefs over the future. And indeed, over the course of training, we find exactly this neural activation geometry. This is just like linearly embedded in the residual stream of transformers, and in fact, for whatever architecture you end up using. So this is the work that we kind of have been building on, and many different directions from NeurIPS in 2024. And I think it might be useful for me to say a few things of like, how do you work with these types of models, and how do you build up something testable here? Basically, for any hidden Markov model, it's just a very simple, like 0-1 random process. You can think of, okay, these transition matrices, the elements are something like joint conditional transition probabilities of if I was in hidden state S, then what's the probability of observing token X and moving to the next latent state S prime? That's what these labeled transition matrices, I don't know if you can see my cursor, but T0 and T1 would be specifying. And the important point is that then if you had such ground truth, you could then figure out the probability of any token sequence, so of any particular word here is just like sequence of tokens. You can just do that by matrix multiplication. So you would start with some initial distribution over your hidden states, over the latent space, and then applying a bunch of transition operators would give you that. So, okay, what does that do for you? Well, this helps us to understand, okay, if I had somehow learned that this is the structure of the world on the left-hand side, but I'm trying to do prediction as well as possible, even if I know that this is what the world is like, but let's say that, you know, I'm just waking up and starting to see tokens afresh. What's my best prediction? Well, one way to predict as well as possible would be to start in, say, the stationary distribution over these latent states. I'm going to now draw a graphical representation of my beliefs, basically my distributions over this thing. And then as I observe more tokens, that gets updated. So my predictions about the future get updated as I see that. So there's kind of this meta dynamic of how my beliefs evolve, which is kind of on top of my understanding of the generative structure. And so this is saying, so there's this belief meta dynamic for how my beliefs evolve. And on the bottom right here, this is just saying, okay, this is just Bayes' rule with linear algebra. So this is kind of how I would move to the different states of knowledge. But then this graphical structure also has an implicit geometric embedding. Easy way to see that is, okay, well, there's just 3 states of a generator here. So every distribution over those states lives in the 2 simplex, basically saying how much probability of each of those states. There's this 3-dimensional thing, but probability is conserved, so it restricts you to this little triangle here. And so then if I was predicting this process, my belief states would naturally lie in this 2-dimensional simplex here. Right? And I'll just say that these beliefs correspond to predictions not just of the next token, but of the full future. So if we believe this was going on, then would kind of induce models predicting something about the full future. Right? So hopefully this makes some sense. Feel free again to stop me if not. So how would we find this in a neural network? So we basically just let's take the transformer architecture as a test case. So transformer architecture, of course, has repeated layers of attention and feed-forward network, MLP. And the residual stream is just the name we give to this kind of vector space that goes all throughout the layers. Okay, so if I put in any particular context or any particular sequence of tokens, that should induce some point in this high-dimensional vector space of activations across layers. So some context will induce some point here. So B is just this cartoon. So like a context will induce some point there. But all the different contexts will induce different points in this vector space, and they'll have some relationship to each other. And then our claim is that they'll have, the relationship they'll have is this belief geometry. So we can look for that, for example, by seeing if there's a linear map from the activations in that high-dimensional space to the anticipated belief geometry. So there's just a cartoon of this, but then indeed that's what we end up finding. And actually you can just do like principal component analysis on the activations, and you end up finding this too in the first 2 or 3 PCs. So this is great. We have some grasp of what models are doing, that neural nets, if they're just pre-trained on tokens, they're doing something like belief updating on a minimal generative structure of their training data, right? And then just one other point I want to make with that is, so here's just another example of a generative structure for, this is the case of, basically you can think of, to generate this, you would flip a coin, random 0, 1, you flip another coin, and then you output the XOR operation of the last two. And then you repeat this, and the phase is unknown. Okay, so again, even if you knew this is the structure of the world, it was this random XOR process, if you then want to predict as well as possible from a fresh context, you'd have to go through these different beliefs where there's kind of different substructures of ambiguity that you need to resolve. You can see that in kind of the green states of uncertainty that you go through in that belief metadynamic. And one thing that I want to point out here is that many of these different belief states have identical distributions over the next token. But to predict the far future, well, they need to be distinguished. And so then here's the geometric embedding just projected down to 2 dimensions here, because this lives in 4 simplex. What we end up finding is that transformers and also other neural networks, they end up distinguishing these beliefs about the far future, even if the next token distribution is identical. So that's an important takeaway from this work. So okay, we kind of laid out this theoretical anticipation that you have this belief geometry, but this was really model agnostic. Like, we weren't inspired by transformers at all in this. And belief states update iteratively. That's the natural way of thinking about it. So how the heck do transformers do this? Since transformers are inherently parallel rather than recursive. So this is kind of breaking our intuition. So we looked into this, led to this constrained belief updating paper that Mateusz led the bulk of the work on this, but it was really beautiful to see how much level of detail we could anticipate. That basically say, okay, well, how the heck are transformers doing this? We ended up being able to anticipate not just if you look at a single layer of attention in MLP, not just the final representation, which is this belief geometry, but even before MLP, that we could then anticipate a different fractal geometry. And so what's the story on this? Just very briefly, this top left part is just kind of a cartoon of what would belief updating look like. If I'm trying to update my beliefs of the latent state of a generative model as I observe tokens, you'd have a belief and you update it as you go along, right? Well, attention doesn't really allow for that. It's fundamentally parallel. So we can say, well, if you were trying to do as well as you could with belief updating, maybe you would just kind of take the Bayesian updates locally and somehow incorporate those. So we kind of established in our previous work that really what the model wants to do is get the distribution over the latent states, given the full history, given the full context of tokens. But what the model has access to by attention is just kind of this pairwise thing. And so there's kind of this, you could incorporate just these updated probability distribution of the destination latent, given the source token, and to kind of make updates locally like that. And then we can say, okay, well, if we just write that down with linear algebra, this is basically then saying what's the new distribution over latent states given the full history or given just those local updates. The linear algebra immediately gives a anticipated geometry. So then we anticipate, okay, well, if the model is doing this, it should have some representation, not just this final belief geometry in the middle column there, but on the left, it's kind of pairwise updates would do this. And then we just do PCA in the model, and what we find is like kind of strikingly good, I would say. Of course, there's some discrepancies, but this is pretty encouraging that we have some handle on what's going on. And then you can write down some equations to say, okay, so what's going on here? On the left-hand side, I have things about the neural network architecture. Like I have the embedding, I I have attention weights and OV vectors. And on the right-hand side, I have kind of the math of Bayesian updating. And when I write these down, it implies kind of a consistency equation, and then you end up getting these kind of spectral decompositions and all that. You get a consistency set of consistency equations that then allows us to anticipate what's the embedding of the tokens, what are the OV vectors, and all of this is borne out really nice, and it implies some algorithm for how the neural network kind of solves the task of prediction by doing updates in the probability simplex over the latent states. And I'd say take a look at the paper if you're interested. Basically, we can anticipate the attention pattern and all this stuff in a lot of detail. Speaking of discrepancies, there's like one discrepancy that what's the heck's going on? Once we had a handle on this, I'm like, okay, if you don't have a beginning of sequence token, like things change in this subtle way. But again, this kind of understanding is building on itself. And just like one more kind of cool mechanistic insight here was that because the model was trying to effectively implement this spectral algorithm of a spectral decomposition of what the transition dynamic was doing, we were able to anticipate like when does a model need more than one attention head and all sorts of detail that unfortunately I don't have time for now. So let me summarize this part and say a little bit about how an intuition for quantum can help us out here. So, okay, first of all, there's something here when I'm talking about the geometric relationship between activations. The kind of interesting geometry is about points being embedded non-orthogonally. The different contexts put you into some non-orthogonal relationship, which is important that neural networks are actually utilizing this non-orthogonality. There's often a story like, oh, well, neural networks would like to represent everything orthogonally, but they can't, and for that reason, you get them to a higher dimensional space in Johnson-Lindner-Strauss and ReLUs and all that. But it's important to recognize the neural network is actually wanting to put different contexts that induce similar predictions about the future. It would make sense for those to be non-orthogonal to represent similarities in different ways. So that's one of the insights that we get from our work. And then there's this thing about neural networks transcending the classical paradigm of computation. Let's see if I can convey that in like 5 minutes. So if you're interested in this, we have a recent archive paper that you can look at where neural networks leverage nominally quantum and post-quantum representations. And let's see, I'm just going back to see a question here from Devin, which was, I guess, a while ago, so sorry about that. Can you elaborate on what the nodes in the meta-belief graph encode? Hopefully that was clear by now, but you can think about them as probability distributions or probability densities over the full future, but more immediately when you're trying to calculate these, they represent probability distributions over the latent states of the model. So hopefully that is clear. So let me just take a few minutes here to point at this work where neural networks somehow have this nominally quantum and post-quantum advantage. This really isn't so much about classical versus quantum as it is about our kind of assumptions or paradigms of classical computation and quantum computation. So, usually you think of classical memory states are these kind of like mutually exclusive things that you just have your basins of attraction for the different memory states. You're in, say, the 1 or the 2 state. You're not in some superposition of those things. You can have uncertainty, but that just fills out the simplex from discrete number of points. Quantum computation, a lot of the benefit there is that you can have this continuity of vector space that we can take, of course, linear combinations of, say, the computational basis states of 0 and 1 for a single qubit. And so properly normalized 0 plus 1 is this plus state. That's different from 0 minus 1, which is minus state. but basically, qubits in quantum memory can take advantage of pure states being non-orthogonal, right? But as I already alluded to, neural nets, they're effectively in this real vector space, so they can also take advantage of this non-orthogonality. So once we had established our result about neural networks can update beliefs over this probability simplex, well, they should also, when it's advantageous, be able to take advantage of more exotic representations. So for example, there's sometimes if you had access to quantum memory, you could do belief updates over that representation of the world, and you could use way fewer dimensions than otherwise necessary. So on the bottom, here's kind of what's going on. There's the stochastic process, the correlated random variables, which is kind of the ground truth, and that would give some ground truth beliefs on the right. Okay, but for the purpose of if you're training a network, the stochastic process generates some token sequences. You're going to train a network on that. You get some neural activations, and then the claim is that there's a linear map from neural activations to a belief geometry, which is basically very close to what we anticipate here. This slide's just to say that there really is a difference between what you can achieve in finite dimensions if you allow yourself a quantum world model rather than a classical, and even if you kind of generalize beyond what a quantum state can be, just like if you allow beliefs to be represented as some convex subspace of a vector space, you get these generalized probabilistic theories. Anyway, there's these dimensionality advantages you get, and neural nets are able to take advantage of this, is the point. So without too much time, I'll say, okay, you guys are probably familiar with a qubit. If I thought if I had a representation of my data generator, which came out of, say, measurements of a qubit, then as I observe more tokens, I could be, say, my belief state could be moving around the block sphere, for example, right? So I could think of the quantum state as a density matrix, or I could kind of unravel that into a block vector. And in general, you can think of a generalized block vector that represents my beliefs. Then we train a process on, this is just classical data, just classical sequence of tokens, standard pre-training. This is a case where there's no finite hidden Markov model that would generate the process, but if you had a single qubit of memory, you could do it. And then what the transformer ends up learning is exactly this belief geometry, as if it was doing Bayesian updating over the states of a qubit. And in fact, this isn't just transformers, it's LSTMs, it's whatever neural network you want. So there's a sense of universality we've been able to find for any neural network. What's it trying to do? It's trying to identify kind of a minimal generative structure of its data, and then it's trying to do belief updating to say, where in idea space am I, right? So kind of zooming way out to large language models, this is something like the model is trying to home in on its user, like who am I talking to? What's my task? What's going on in this world? And there's a belief updating structure there, which is of course just like much more sophisticated. But we can take this as a bit of inspiration that we have a handle, at least in some toy settings, for what's going on. So now we should see where this breaks, right? So this is hopefully up to you guys. If you're feeling inspired, you should find where this stuff breaks and refine and develop the tools, hopefully find some belief geometry in large language models would be amazing. I'll just close with a few open questions in case that's useful for you guys. So directly from the work we've done, there's a few opportunities for, we did anticipate this belief geometry, but we're still, to be honest, very confused of why that belief geometry is represented linearly rather than, I don't know, some other nonlinear thing, for example, some log geometry that would make a lot of sense, or maybe that also coexists, would make sense to check for that. The constrained belief updating paper that I pointed to, So we did that for this kind of MES3 process, is what we call it. That gives this triangle fractal. But if you did something analogous for the random-random XOR process, I think you'd need at least 2 layers, but I think that'd be really insightful for discovering a few more things. Taking a step back, how do models approximate the world? So if you believe that models are trying to represent beliefs over a world model, the residual stream is not going to be big enough, so somehow this needs to be factored, right? And so what does that look like? And can you find belief geometries in large language models? Maybe you can leverage SAEs, for example, to think of SAE features, the time series of those. Could we use those in a clever way to identify belief geometry? So by thinking about physically embedded AI, the fact that agents are physically embedded, we could think of, well, what's the information theory of communication through real vector spaces? So is there something analogous to thinking of symbols and communication channels as these continuous things? So it would be more akin to quantum information theory, but it also doesn't have those constraints. So I think there would be something useful to learn there. There's something about this Platonic representation hypothesis. Does the physical world tell us how it should be represented, and up to what invariance? And people talk about, if we study this problem hard, then we can just guarantee that the outputs of AI will be safe. But their behavior, just as ours, is in this chaotic, complex world, and you can, of course, have proofs that there's a finite predictive horizon. So what does it mean that we're guaranteeing safety? It seems like a challenging problem, but would be interesting to think about that if you have some relevant background. And then finally, maybe using physics as an analogy also opens up some opportunities. So in non-equilibrium thermodynamics, there are these really powerful fluctuation relations that seem quite relevant for saying, how likely are you to go, to maybe this part of the weight space versus that part of the weight space. I think that could be adapted pretty straightforwardly. And then also, not everything needs to be about interpretability, right? So we can think of, okay, as we have AI agents that are interacting with each other and with humans, what collective dynamics can we anticipate, and can we steer? Maybe we can tweak the interactions to make the collective dynamics better. If you're into complex systems, this might be a nice sort of project. So I think I'll kind of just end here. This is just recapping the virtuous cycle. Intelligence is physical, and if I have time for questions, I'd be happy to chat with you guys. And if not, also can chat in the office hours.
Yeah, thanks a lot, Paul. Sorry, I didn't want to interrupt you in the middle of the presentation, so I didn't drop the questions. But yeah, really interesting presentation. And yeah, thank you so much for all the advice and thoughts as well. I think one question here is, can you elaborate on this takeaway that a far future beliefs, have you taken this up already? No, right? Far future beliefs and the next token beliefs are separated. What does the evidence for this come down to? And they have 2 other questions as well, but do you want to take this one first?
Yeah, I appreciate the questions here. So I'll start with this first one. So there's 2 different things. One is, how do we establish that transformers and other neural networks are keeping track of their expectations or probability distribution over the full future rather than just the next token? And then there's what's the takeaway from that? So the first, so for the first point, I'll maybe just point again to this random XOR process where, so in this case, there's many of these. This is this kind of belief metadynamic structure on the right that I laid out. This is, if you were doing optimal prediction, this is how you would do it in this recursive fashion. but many of these states have identical, like say 50-50 expectations over the next token. And so we can say like, okay, these belief states are separated in the 4 simplex over the latent states, even though they would be collapsed over the 1 simplex of zeros and ones. And then what we end up finding, so we can just check that indeed the model, it was a transformer in this case, it does choose to distinguish these beliefs about the far future, even though it was, just very explicitly, it was just trained on next token prediction. So why does this happen? I think if it was a recurrent architecture, it'd be more obvious. There's still there's a way of thinking of transformers which feels kind of recurrent in that it can look at, of course, its activations at layers and positions behind it. But you can think that, even if the next token is the same, if I kind of lose some information that will eventually be relevant to the next token, then I should keep that around. That's kind of the idea. But then the takeaway, maybe high level, is that these models are maybe more powerful than you'd think. Like they're, I'd say, with gaining something like a world model and doing belief updating over that, what it tells me is that pre-training is sufficient to effectively gain an understanding of the world and basically predict everything as well as possible. Like if you throw compute at me for pre-training, I'm just going to understand everything as well as possible. And that's the best possible infrastructure to then do any task subsequently. So another part of following up on our work would say, like, how does this change with fine tuning or RL on chain of thought? And that'd be pretty cool, I think, to also see, like, how does the belief geometry change as you do that stuff? So hopefully that addresses at least part of your question there. I see the question of what might belief geometry for an LLM look like? Yeah, it's a great question. So I've been thinking about this a lot lately. And the whole thing is going to be massive, right? But I do anticipate, and we have some preliminary results showing that belief structures really should factor. And so for that reason, I'm encouraged that you can kind of look at some kind of substructures. Like you can probably probe, like I was saying, with SAEs, or maybe particular context that homes in on a particular kind of belief substructure. And I do anticipate there will actually be some like quite simple, like low dimensional belief structures, fractals. Sometimes it'll be kind of classical looking, sometimes it'll be post-classical. But we're just starting to go down that path, and it'd be, I think, really cool to try to vibe this up if you're feeling encouraged, and especially if you're comfortable with working with LLMs.
So I missed you said something about how the quantum picture that you found was not related to the generating the same HMM, or maybe I misunderstood this. Could you talk a little bit more about how that was generated?
Yeah, let me say a bit more about that. I was nervous about time and probably went too fast, and so it was not helpful. So the idea here is that there are some processes, so classical stochastic processes, just sequences of tokens, that there's no finite hidden Markov model that can produce token sequences with this distribution. However, if you had a single qubit of memory, then by doing just like standard kind of quantum instrument evolution and measurements on that, it could produce the process. And so there's been a sequence of papers on this in the last decade or two. I used to work on this stuff a little bit in physics too. And so we just took like an example process from there where you can have a single qubit of memory, but it would require an infinite state HMM. And then we just train a neural network on the token's output in the case where a single qubit is sufficient. And then what we end up finding is exactly that the neural network learns to represent beliefs over the state of a qubit. So I'm not sure, Lauren, if that was answering your question sufficiently. I'm happy to elaborate if.
Yeah, thanks.
Okay, awesome. We do have another speaker as well, and I don't want to, I don't want to go too much over time, so I'm wondering if
Sure.
it's fine to, have you like comment it out if possible.
Yeah, I am happy to reply to comments in the in the comment thread there. So awesome. Well, yeah, thanks for having me, and I'll
Yeah,
be
thank you so much.
I'll be at the office hours later if you guys want to chat.
Yeah, awesome. Thank you so much, Paul.
Thanks a lot, Paul.
Yeah, awesome. Thank you. I think Dimitri is still around. I'm gonna ping him, but yeah. Awesome. Thank you so much, Paul. I'm just gonna invite him to speak. Hey, Dimitri.